All right, let's dive into one of the coolest and most powerful things calculus can do. Figure out how to measure the volume of pretty much anything, no matter how weird or complicated its shape is.
I mean, think about it. We all learned the formulas for a box or a can back in school. Super simple. But look around you. The real world isn't made of perfect blocks. It's full of curves, strange shapes, and irregular forms. So how in the world do you find the volume of those things?
So here's how we're going to tackle that. We'll start by seeing why basic shapes just don't cut it. Then, we'll uncover this awesome trick I like to call the secret of slicing. After that, we'll build some 3D shapes, check out the calculus tools we need to measure them, and finally we'll use all of that to solve a famous, impossible problem.
Okay, first up, beyond basic shapes. Let's really get why the old school formulas we know just aren't enough.
Yeah, those formulas for cubes and spheres are great, but they're really the exception, not the rule. Most things you see every day, from a coffee mug to a part in a car engine, have all these curves and contours that simple geometry just throws its hands up at. We clearly need a better, more powerful way to handle them.
And that brings us right to the main event, the secret of slicing. Honestly, this is such a simple, brilliant idea, and it is the key that unlocks everything else we're going to talk about.
Okay, I know this sentence sounds super technical and intimidating, but trust me, the idea behind it is something you already understand. Let's forget the jargon and just break down what integrating the cross-sectional area actually means in plain English.
So, picture a really weirdly shaped loaf of bread. You can't just measure it with a ruler. But what if you sliced it into a whole bunch of super thin pieces? Each individual slice is a simple shape, right? It's basically a flat circle or a square. And you can calculate the area of that slice. Well, if you could just find the area of every single one of those slices and add them all up, you'd have the total volume of the whole loaf. That's it. That's the secret.
And this formula? It's just the fancy math way of saying what we just did with the bread. The volume V is equal to the sum of the areas A of all the slices. That squiggly symbol, the integral, is basically just a stretched out S for sum. We're literally just summing up an infinite number of impossibly thin slices.
So now that we have this idea of slicing, let's look at a really cool application called solids of revolution. This is where we can create all sorts of complex 3D shapes just by starting with a simple 2D line.
Imagine you've got a simple curve drawn on a piece of paper. Now picture spinning that paper really fast around an axis, kind of like a potter's wheel. The 3D shape that the curve traces out in the air, that's a solid of revolution. A simple little curve can suddenly become a beautiful vase. A boring triangle spins into a perfect cone. It's a pretty amazing way to generate complicated shapes.
Okay, so we know how to make these cool shapes, but how do we measure them? Well, for that, we've got a special calculus toolkit with 3 main methods to choose from. Here are our 3 main tools, the disk, washer, and shell methods. The disk method is your go-to for solid objects. The washer method is for things with a hole in the middle. Think of a donut, or, well, a washer. And the shell method is just a different way of slicing that can make life way easier in certain situations. It really is just about picking the right tool for the job.
Let's start with the first one, the disk method. This is the most direct use of our slicing idea. You're literally just imagining your 3D shape as a stack of an infinite number of paper-thin coins or disks. You add up the volume of all those little disks, and you've got your total volume.
And the formula makes perfect sense when you look at it. We all know the area of a circle, right? Pi times the radius squared. Well, this formula just says the total volume is the sum of the areas of all those little circular disk slices. See? It's just our bread slicing principle, but now with circles.
And the washer method? It's even more straightforward. It's literally just the disk method, but for an object with a hole. You just find the volume of the big outer disk, and then you subtract the volume of the little hole you're cutting out of the middle. What's left is the volume of your washer. Simple as that.
All right. We've got the theory, we've got the tools, so let's actually put them to work. We're going to take on a classic problem and measure something that, without calculus, is a real headache to figure out from scratch.
So how does anyone actually prove the formula for the volume of a sphere? Where does it come from? Well, watch this. We start with a super simple 2D shape, a semicircle. Then we take that semicircle and revolve it around the x-axis. And what shape do you get? A perfect sphere. So now, all we have to do is use our disk method to add up all the little circular slices from one end of that sphere to the other.
And when you do the math, when you actually work through that integration, this is what pops out. 4/3 pi r cubed, the famous formula for the volume of a sphere. It doesn't come out of some magic geometry textbook. It's derived directly from this fundamental idea of slicing and summing. That's the power of calculus right there.
Now this whole slicing idea doesn't just stop with volume. You know, the stuff inside the shape. We can actually tweak it a little bit to measure the stuff on the outside too. To get the volume, we added up the area of all our slices. But to get the surface area, we just add up the circumference of all those same slices.
So that exact same core logic, break something complicated into an infinite number of simple little pieces and then add them up, can also be used to find the exact length of a curvy line, which we call arc length, and it can find the total surface area of those solids of revolution we were making. It's an incredibly versatile concept.
Okay, that was a lot, so let's zoom out and pull everything together. What are the big ideas you should really take away from all this?
First, and this is the big one, we can measure crazy, complex shapes by breaking them down into infinitely many simple slices. Second, we can create a lot of these shapes by spinning 2D curves to make solids of revolution. Third, we've got a toolkit, disk, washer, and shell to do the actual measuring. And finally, remember that this whole slice and sum idea is super flexible. It works for volume, but also for a curve's length and its surface area.
And that really gets to the heart of why any of this matters. This isn't just some abstract math puzzle. These exact techniques are absolutely essential in physics, in engineering, in computer graphics, in product design, basically any field where you have to understand and work with real-world complex objects.
So I'll just leave you with this thought to chew on. The fundamental strategy we used here was to take a big, intimidating problem like the volume of a weird shape and just break it down into tiny, manageable pieces that we already knew how to solve. If that works so well for physical objects, what other huge, complicated, maybe even non-physical problems in our lives could we start to solve if we just used that same approach?